Swayam Prabha. Digital India. Educated India.
So today we are going to learn estimation. What is estimation? Each and every member of the population cannot be tested to assess the population parameters due to time and cost constraint. This is very, very common, The whole population cannot be tested. Suppose I give you 1 ton of cotton yarn, where there are maybe, arbitrarily I'm saying 10,000 cones or cheeses are there. Now if we want to know some parameter about the cotton yarn, is it not possible to test all 10,000 cones or cheeses? It is something which is impossible because of time and cost constraint. So what we need to do then? We need to estimate the values of the population parameter based on samples only. That is, we will take some samples and we will assume that these samples are representative of the population, and then we will try to find out the parameter of the sample, and from those values of the parameters we will try to estimate the population parameter. The population parameter could be, for Poisson distribution, mean. For normal distribution, the population parameter could be the mean value of the population or standard deviation of the populations. For binomial distribution, it could be sample size, it could be probability of success or failure, or number of success in a given number of trials, things like that. We need to estimate the population parameter from the sample. The reason is whole population cannot be tested. And we have two types of estimations. One we call it point estimate, and the other one is called it interval estimate, which is basically confidence limit. So we'll learn about these two estimations. First of all, point estimate. Point estimate uses single number to estimate the population parameter. So we'll estimate the parameter by only a single number. Example, when a sample of size small n is drawn from a normal population, then the sample mean is what? We all know how to calculate the sample mean. It is sigma x by n. So that is an estimate of mu, which is the population mean. So sample mean is x bar and population mean is mu. So we want to estimate the population mean by the sample mean. So sample mean is one number and population mean is also will be one number. Or we want to estimate about sample variance. If we take a sample, then we know how to calculate the variance of the sample, or we can say the standard deviations. Now this is the formula that you have already learnt earlier. So this variance is an estimate of population variance, sigma squared. I think I have already told you earlier that mu and sigma, they represent the population parameters, whereas x bar and s, they represent the sample parameter. Now the question that comes to the mind, how accurate is these estimates are? So accuracy of point estimate. The concept of accuracy or precision is related to the properties of the sampling distribution of point estimate. What is that property? If the mean of its sampling distribution is equal to the value of the unknown population parameter to be estimated, then it is accurate. This statement is very important to know or to understand. Mean of its sampling distribution is equal to the value of the unknown population parameter to be estimated, then it is an accurate estimate. Like if the sample mean, and question is the sample mean an accurate estimate of the population mean? Then the answer is sampling distribution of mean, which is mu x bar, is equal to mu. Mu x bar, that is, if I take large number of sample means, then we will find a distribution of sample means, and this distribution of sample means will have a mean which is equal to the population mean. Hence we say x bar is a good or accurate estimate of population means. This is, we have learnt it earlier based on our central limit theorem, that if we collect samples from any population, irrespective whether the population is normal or not, but if we keep taking samples which are large in size especially, then if we find out the mean of samples and we keep repeating it and find out large number of sample means, and then these sample means we plot, then we'll find a distribution of sample means. We'll get a frequency distributions, and then if we plot it, it will give a beautiful distribution, and this distribution is always normal in nature, and the mean of the sample mean is equal to population mean, and therefore x bar is an accurate estimate of population mean. Similarly, now is a square is an unbiased estimate of sigma square, that is population standard variance. Mean of sampling distribution, if it is not equal to population parameter, then it is biased. Now we'll check it whether the statement is correct or not. It has been shown earlier. You have to look back the previous slides, that this particular ratio n-1 square by sigma square follows chi-square distribution. This was discussed earlier. Now this is what we have to remember, that n-1 square by sigma square follows chi-square distributions. If that is true, the mean of chi-square distribution is the number of degrees of freedom, and which is equal to n-1. The mean of chi-square distribution is equal to number of degrees of freedom, and for chi-square distribution the degrees of freedom will be n-1, and therefore we can write that mean of this parameter is equal to n-1. If that is true, then if I rearrange them, then I can write mean of a square is equal to sigma square, because we can n1, n minus 1, n minus 1 will cancel, and then we go a square by sigma square will be 1, and therefore mean of a square is going to be sigma square. That means the variance, sample variance, is equal to the population variance. So this is the way we can prove that sample variance is an unbiased estimator of population variance. So there will be occasions when, to find out population variance, we have to use the sample variance. So why we are using, if that question comes to the mind that time, then the answer is here. Hence we write a square or the variance, sample variance defined by equation 1 is an unbiased estimate of population variance, which is sigma square. Now come precision of a point estimate. Precision is measured by standard deviations of sampling distribution. Smaller the standard deviation, more precise is the estimate. That means variability is less and less. So standard deviation of sample mean, which is known as standard error also, the formula is sigma by root n. This formula also was told earlier, and you already know what is standard error. So the standard error formula, what is coming? N is coming at the bottom. N is the sample size. Therefore, the error will be less and less if n is more and more. That means large samples will give you a better estimate, because standard error is going to reduce. That means as n increases, standard error is going to decrease. And standard error is what? Is the standard deviation of sample means. So that is a reason that if we want to reduce the error, we have to go for large number of samples. But because of many other reasons, sometimes we may not be able to take large number of samples, or whatever it is possible, we should try to go for more number of samples. Now comes confidence limit for population mean. So our idea is to find out the population mean. But if we try to predict the population mean from the sample data, then there's every chance that whatever the sample data gives me, that may not be the correct representation of population mean. This is something very difficult. Let us say what we can say about the population mean. Now the variance of population is known to us. Suppose that there is a population whose variability is somehow known to us because of our so to say past experience. We know that typical variabilities in this particular process is somewhere in this range, or a typical value we know in advance. The population mean mu is unknown and it needs to be estimated. This is what we need to estimate. How to go about it? Let the observed mean of a random sample of size small n is, let us say, x bar O. This O stands for observed. So we take a random sample of size small n and we find out what is the mean. and the value comes, let us say, x bar 0. So bar indicates the mean always. Whenever there is a bar on x, you should read it the mean value of x. So we can say that x bar 0 or O is an estimate of mu. We have already seen it. It is an estimate of mu. But this is not mu. It is highly unlikely that x bar 0 will be exactly equal to mu. And even if it happens, we will not know, because the value of mu is unknown to us. For the population, what is the value of population mean? We don't know. So if we get a sample, find out the mean, then also we'll know whether this mean, sample mean is exactly equal to the population mean or not. There's no way to know it. The best that can be done is to produce two limits between which the unknown mu is expected to lie. We will never be able to tell that this is the exact value of population mean. This is something which is impossible, but we can try to find out the limit, the two values, a lower value and an upper value. And we can say, with a certain level of confidence, that the population mean is going to lie between these two values. These limits, the lower limit and upper limit, they are known as confidence limit. That is what is called confidence limit. Now, why the confidence word is coming? We'll be coming to that now. This diagram that you have seen earlier, this is the diagram. What? This is the distribution of mean, that is x bar. And this distribution is always normal. Whether the population distribution is normal or not, sample mean distribution is always normal. To consider the distribution of means. So I have shown here the distribution of means, which is symmetrical and it is normal. So mean of sample means, we write is at mu x bar is equal to the population mean, and standard deviation of sample mean is equal to sigma by root n. So this point is mu x bar, which is equal to mu, and standard deviation of this is written here, sigma by root n. So sigma x bar is sigma by root n. We have to find out two limits equidistant from the mean, such that the tail area of the distribution are both equal to alpha. So we have to find out these two limits here from the mean, equidistant from the mean. The mean is here, population mean, and this sample mean of sample mean is also at the same place, but they are equal, which is unknown to us. From here we make two limits which is equidistant on the right hand side and left hand side, such that the area beyond the limit is alpha this side and alpha on the other side also. The distribution of x bar being normal, the distance of the limits from the mean will be how much? Z alpha sigma x square, sigma x bar. Sigma x bar means it is the standard deviation of sample mean. So whatever value of alpha we choose, we have to find out what is the corresponding value of z for that alpha, which we will get from the standard normal distribution table. So for a given value of alpha or a given value of 1 minus 2 alpha, we have to consult the table, standard normal distribution table, and find out for alpha what is the value of z alpha here, what is the value of z alpha here. So z value for a given alpha, we write it as z alpha. So alpha could be 0.01, alpha could be 0.05, alpha could be 0.025, whatever value of alpha you choose. Correspondingly, we can find out what is the value of z, and therefore the distance from here to this is going to be that z multiplied by standard deviations. So z alpha can be found out once alpha is fixed. So alpha we have to fix in advance, whatever value of alpha. Now the limits will be how much? So from here to there, the distance is, right hand side it is mu plus this side, so it is this much. And on the left hand side, the z values are negative, so it will be mu minus this. So these two will be the limits, upper limit and lower limit. Mu minus z alpha sigma x bar, mu plus z alpha sigma x bar. These are the two limits. When a sample is drawn at random, the probability that the mean will lie between the limits, that x bar is going to lie between the limits, can be written as how much this probability that x bar is going to lie between upper limit and lower limit. This is the lower limit, this is the upper limit, is 1 minus 2 alpha, because we have chosen this to be alpha, and this from here to there, the area under the curve shown by the violet color is 1 minus 2 alpha. So the probability that x bar, sample mean, is going to lie within the two limits, the limits have been defined, is going to be therefore 1 minus 2 alpha. That means we have 1 minus 2 alpha level of confidence we have in saying that x bar is going to lie between these two limits. From there, the same equation we are writing it here also, there's no change. Now we take this part. Here what is x bar is greater than mu minus z alpha sigma x bar, and therefore this is equivalent to writing mu is less than x bar z alpha sigma x bar. What I am doing it, I am just simply transferring this part to this side, that's all. So you can write this is equivalent to this. Similarly, if we take the right hand side limit, which is here, we can write mu greater than x bar minus z alpha sigma x bar. So it is simply rearrangement. So equation 2 is therefore equivalent to what? X bar probability of sample mean lying between these two limits is equivalent to saying population mean lying between these two limits. That probability almost exactly will be same. So the same statement we are simply changing the position of the variable. X bar was at the middle, now we bring mu at the middle, because mu is what is unknown to us. X bar we will be able to find out by taking a sample. So from here, as we come to equation number 3, we can say that the probability of population mean lying between these two limits, the upper limit and the lower limit, is going to be 1 minus 2 alpha. And therefore, these two becomes my limits, upper limit and lower limit. Or we can say that is what is confidence interval. And then what we do here, these are the two limits. This is nothing but this part is coming here and this part is coming there. They become my limits. And in the next equation, what are you doing? Sigma x bar, this is what we are changing by sigma by root n. Because we know that standard deviation of sample mean, which is called standard error, is sigma by root n. Sigma is the population standard deviations. And in this case, we have written at the beginning that the variance of the population is known to us. So the value of sigma should be known to us. This is how we will be able to say that the population mean is going to lie between these two limits, the lower limit and upper limit, with a level of confidence 1 minus 2 alpha. If alpha is chosen to be, let us say, 0.05, then 2 alpha is 0.1. So 1 minus 0.1 is 19.99. That means in that case, with 99% confidence, we will be saying that this mu is going to lie between these two limits. And commonly accepted value of 1 minus 2 alpha is 0.95 or 0.99. So if we say 0.95 is the level of confidence, then 0.05 becomes, it is a chance that the population mean may not lie within these limits. There is no certainty. There is only a probability. So if we calculate these two limits, then we will say with 95% chances there, it is going to lie within this limit. And 5% chance is there that it may not lie within these limits. The same thing we are now showing it here, whatever we have discussed earlier. In this diagram, 1, 2, 3. So this is the population mean, where it is going to lie. And these are the two limits on the right hand side and left hand side. Let us say I have chosen a value of 1 minus 2 alpha to be 0.95. And corresponding to 0.95, if we go to find out what is the value of z, or alpha value will be, in that case, is going to be, I think, 0.025. And corresponding to 0.025, if we try to find out the value of z, it will give a value 1.96. So it is 1.96 this side minus 1.96 that side. And let us say I find out, so this is about the distribution of x bar. Now I take a sample and find out the value of x bar. This x bar is going to be, this is basically your x bar. X-axis is representing x bar. So a typical sample mean may be anywhere on this x bar line. I take a sample, it can fall anywhere. Now suppose it has fallen here, shown by this small blue circle. X bar is there. Now from x bar, if I draw the same limits, I start from whatever x bar is there, it is here. This is my X bar that we have found out. And then if I draw the limits on both sides, 1.96, 1.96 both sides, then you see that when it is falling here, I can say that within X bar plus minus 1.96 sigma X bar, the population mean is going to lie, because this is the extreme when it has fallen on 1.96 sigma X bar line. If it falls here or it falls here, it falls here, and if you draw the right hand and left hand side limits, if we show, it is going to cross the point where mu is lying, population mean is lying. That means wherever X bar is going to fall, here, there, here, here, whatever it is, we can say with 1.2 alpha, this much certainty that the mu is going to lie there. So the value of X bar, somebody may get a value here, someone can get a value here, someone can get a value here, someone can get a value here. So this is what I am representing the same concept on this slide. And now we'll solve a problem so as to reinforce the concept. Let us say the feel of a fabric is rated in a scale 1 to 5, with 5 being excellent and 1 means very poor. From a random sample of 36 customers, the average score was found out to be 3.5, with standard deviation 0.8. Obtain 90% confidence interval for the population mean, or the mean score of all customers. So what is the 90% confidence level? At the confidence level of 90%, what is the limits within which the population is going to lie? Population mean is going to lie. This is what we try to find out. So what will be the approach? The problem solving is very easy. If you understand the concept, then it will be very, very easy. Solution, we start. Wherever possible, we can draw a diagram on normal distribution and put your values in the respective places so that it becomes easy to comprehend and solve the problem easily. So what is given here? The value of X bar is given 3.5. Value of sigma is also given 0.8. Level of confidence is given 90%. That means this 1 minus 2 alpha value is given, which is 0.9. 90% basically means 0.9. So what is the value of alpha? 0.05. Now for alpha 0.05, what is the corresponding value of Z alpha? That is Z 0.05. That value we have to go to the table and find out. I have already shown you the tables earlier. You have to consult the normal distribution table, standard normal distribution table, and in that table you will find that for different values of alpha, the Z values have been quoted. Now for a value of alpha which is 0.05, the value of Z is 1.6449. Now standard deviation is given, which is 0.8. But what is the standard deviation of the sample mean? That is sigma X bar. which will be sigma by root n. So 0.8 by root over 36, which will be 0.133. And now comes the confidence limits. Are the two limits within which the population mean is going to lie. So right, it will be x bar plus minus z alpha sigma x bar. This is the formula we have already given, plus and minus. So x bar is 3.5, x bar is the sample mean, which is 3.5, z value is 1.6449, and value of sigma x bar is 0.133. It is 3.5 plus minus 0.2187. So lower limit will be 3.28, upper limit will be 3.718. So within these two values, 3.28 to 3.718, the population mean is going to lie. That is what we can say, and in saying so, we have 90% confidence level. That means if I say so, out of 100, 90 times I will be correct, 10 times I may be wrong. Next question comes, okay, when the population standard deviation is not known. Earlier we assume that the population standard deviation is known to us. But when it is unknown, then what do you do? First case is sample size is large, more than 30. In that case, one can estimate the limits by replacing sigma by sample standard deviations S. In this case, this is what can be done, and therefore the limits will be same formula. Sigma has been changed by S. Rest remains same. Is x bar minus z alpha s by root over n, x bar plus z alpha s by root over n, where s is the sample standard deviation. So sample standard deviation is going to be an estimate of population standard deviations. And the other thing could be where n is less than 30. Many a times, obviously, we may not be able to have 30 samples may not be tested. So when n is less than 30, the sample standard deviation will be imprecise estimate of sigma. Provided population is normal, the error can be reduced by replacing z alpha by t alpha now. That is t distributions. So you have also learned earlier what is t distributions. T distribution is a little different from the normal distributions, and t distribution approaches normal distribution when the n is very large. So when n is less, then instead of finding out z alpha value, we find out t alpha values. The rest remains exactly same. So now the limits will be x bar minus tk alpha, x bar plus tk alpha. K is the degree of freedom, alpha is the 1 minus 2 alpha is the level of confidence that we want to keep, and S is sample standard deviation, and N is the sample size. So everything remains same. Simply Z is replaced by Tk alpha. Alpha is level of confidence. It will be 1 minus 2 alpha. K is the degree of freedom, n minus 1. now again we'll solve a problem where the n is not really so large, and let us say calculate 95% confidence interval for population mean for a sample of size only 7. So n is much less than 30. The sample data is 1, 2, 3, 4, 5, 6, 20. So these are the values. 7 data we have, and the values are 1, 2, 3, 4, 5, 6. The 7th reading is 20. So what is the mean of this sample data? This is what it is, which is 5.85. So X bar is in this case 5.85. And standard deviations can be calculated, and it is 6.46. Sample size is only 7. So we have to use T statistics. So this is what is X bar. This is your S. N is much less than 30. So we have to go for T statistics. And confidence limits, as we have seen in the previous slide, one is upper limit and lower limit. So we have to go for plus minus X bar T K alpha S by root over N. And if we try to find out this values, this value I have calculated, this value I have calculated. This T value you have to get from the T table. So you have to consult the T table for a given value of alpha and degrees of freedom. So K is going to be, in this case, 7 minus 1, 6. And if we consult the T table, we'll get a value which is 2.45. So this value is coming from T table. It is not suddenly appearing from nowhere. It is coming from T table. And we just do this normal simple calculations step by step. The limits are this and this, 11.82 and minus 0.12. So these are the two limits. When sample size is low. So that's, you see, the calculations are only 4 or 5 lines. That's all. And with a calculator in hand, you can do it very fast. So this is the limit of mu in this case. After this, we come to two very interesting points now. One is sample size determination for the while calculating mean. What is the sample size we should have? How many sample data we should have? Precision of an estimate is measured by the confidence interval, and that depends upon the size of the sample. So confidence interval, we have seen it. This is the formula that we use. What sample size is required to give the required precision? Suppose the precision of the estimate is such that the confidence limits are X bar 0 plus minus E, where E is the tolerance. So we want that the population mean should lie between X bar 0 plus minus capital E, where E is the tolerance. So it could be, let us say, the count of yarn we want to find out in a cheese or cone. or we want to find out the GSM of a fabric, and we say that count value, another example I am saying, should be 30 ticks plus minus 1 ticks. So my tolerance is 1 ticks only. Someone can say, I am ready to give tolerance 2 ticks. So it will be 30 plus minus 2 ticks in that case. In some cases, so tolerance could be more, could be low, could be high, whatever it is somebody wants. So whatever it is, we are representing it by capital E. If it is so, then E becomes this. See, interval is this much, and the plus minus part that we see here, that becomes my E. That is my tolerance. So E is this. From there, I can find out what should be the sample size, small n. Using the same equation, we can write n equal to z alpha into sigma by E whole square, because n is coming under root. So from here we can go there, and this is how the sample size can be determined. So n is a function of the level of confidence alpha that you want, first of all. At what level of confidence you want to say. So that is whether you want 95% confidence or 90% or 99%. It depends upon the standard deviation of the population also. And it depends upon the tolerance. The narrower the tolerance, small is the value of E, more will be the number of samples you will require. So if I want to keep the tolerance low, I need to take more number of readings. N has to be very, very large then. So this formula is used to find out the sample size. And I can use the left-hand side formula to find out the tolerance. If tolerance is not given, then I can also find out tolerance. Now, one more numerical problem related to this topic. A textile engineer collected data on the operator's time to sew a collar. Based on 52 operators, it was found mean to be 1.865 minutes, with standard deviations 1.250. What one can assert with 95% confidence about the maximum error if x bar is 1.865? What is the error or what is the tolerance? Meaning same. So tolerance or error basically means same. This is what we need to find out. If x bar is used as a point estimate of the true population mean, so population mean is given, and say that is what is x bar is. So E becomes my plus E upper limit and minus E become my lower limit. So x bar is given here, which is equal to mu. Sigma is also given 1.250. Level of confidence 95%. So 1 minus 2 alpha 0.95. So how much is alpha? 0.025. Find out for 0.025 what is the value of Z. And you will get a figure 1.96 from the table. So this is coming from Z table, this value is coming. You have to consult the table, then only you get this value. For alpha, 0.025. Okay. So now, this formula is equal to Z alpha sigma by root n. So straight away we substitute the values. See, we have all the values with us now. We know what is Z alpha, 1.96. We know what is sigma, 1.25. We know what is number of samples, 52. Operators are 52. So we get 0.339. That will be the error. So this is how we can find out. The formula is simple. You need to find out the relevant values of the parameters, and straight away you have to substitute in the formula to get the answer. Another example we'll take. If we want to be 95% confident of estimating population mean to within sampling error of plus minus 5, and the standard deviation is assumed to be 15, what sample size is required? So in this case, we want to know what is the value of small n. E is how much? From the, it is given already, 5. How much is sigma? Also given, 15. Level of confidence given 95%. So I mean 1 minus 2 alpha, 0.95, alpha is 0.025. For alpha 0.025, Z value is 1.96. So now the formula is in front of you. Use this formula and substitute the values. You get the answer. What is 34.57? So approximately this is 35. So you have to take sample size has to be 35. So confidence limits of proportions. Let us start with an example. Proportion of defective articles produced in a process. Like we produce t-shirts in a garment manufacturing unit, and there could be some defects. Defective articles can also get produced. So point estimate, first of all here, select a sample of size, let us say n, and count the number of defective articles in it. And let us say that is what is XO, and therefore the point estimate of the proportion PO is X0 by N. Out of N, X0 are defective. So the proportion is X0 or XO by N. AO stands for actually observed. So PO stands for P observed, proportion of observed defectives, which is X0 by N. We would like to know where the true proportion is likely to lie. Where the true proportion is likely to lie. Now this is the observed value, but the actual true proportion is where? This value may match, may not match. And therefore here also we can only think of a limits within which the population proportion is going to lie, and the limits we can find out with a certain level of confidence, and hence we say it is confidence limits of proportion. Now you can see the diagram is given here. in the case of true proportional lattice, that is what is P dash. And to find out the confidence limit of P dash, we need to know the sampling distribution of the point estimate. P follows a binomial distribution. If you remember the binomial distributions, that wherever there is a certain defective items are there, or true false type of situations are there, we try to find out how many defective articles are there, or somehow how many defective any type of articles or items could be there. Binomial distribution is the right distribution which is used. So here also it is similar to that, and hence we say that P, the proportion, is going to follow binomial distributions. But when the sample size is very large, binomial distribution can be approximated by normal distributions, provided n is very, very large. And there is a proof behind this. That proof we are not going to discuss here. Now, what is the mean value of binomial distribution? Mu of x is going to be n p dash, and standard deviation is going to be root over n p q. That means n p dash 1 minus p dash. This is the q. P plus q is going to be 1. I think we have discussed it earlier while discussing binomial distributions. Probability of success and probability of failure, sum of these two is going to be 1. So here also, and in those cases, in the case of binomial distribution, the mean is always np. In this case is np dash, and standard deviation is root over npq. So np dash 1 minus p dash. 1 minus p dash representing q. That is success, failure, you can say. Now, the distribution of this mean is shown here. It is also going to follow a normal distribution, because why I am saying it? Because when n value is large, then binomial distributions can be approximated by normal distributions. So that proof we are not going to discuss it here. We assume that, and we will accept it, that binomial distribution becomes equal to or can be represented by normal distribution when n is large. So probability that observed number x0 is going to lie between the two limits, so that the tail area is alpha. The approach is exactly same. Here the mean is np dash. This is the upper limit, plus sign should come here. This is the lower limit, and standard deviation is given here. Sigma x is this much. So area within this is going to be 1 minus 2 alpha, that any observed value of defective items is going to fall within this. It can be this probability within these two limits is going to be 1 minus 2 alpha. And then we replace sigma here by root over n p dash 1 minus p dash, and this sigma x also by this. Same thing we are replacing. It looks little longer, but actually we are not simply changing sigma x by this. Now we focus on the first inequality, on the left hand side inequality. What is written here? That this whole thing is less than x0. X0 is number of defective items observed. So X0 is greater than, as it is written here, you see X0 is greater than this part, left hand side. Same thing I am writing it here. And then we can write by rearranging, the P dash should be less than this value. So first inequality we take and then write P dash, this is equivalent to writing P dash less than this, x0 by n. So I take this part on the right hand side and divide by small n. So after rearranging the equations, we can write that the previous statement was x0 between these two limits, such that the area on the outside the limit was 1 minus 2 alpha. Same, alternatively, it can be written as P dash lying between these two limits. So the inequalities have been changed and we can bring P dash at the middle and we can find out the P dash lying between these two limits on the right hand side and left hand side limits is 1 minus 2 alpha. And therefore, the confidence limits are x O by n plus z alpha P dash 1 minus P dash by n. That is the confidence limits for the proportion. Now here also there is a little issues are there. What is that? In the above expression, in this expression, the population proportion P dash is unknown. So in this equation, where I writing the confidence limits are xo by n plus z alpha root over P dash 1 minus P dash by n, but we don't know the value of P dash because that is the population proportion defective items. But this can be replaced by P0 in most of the cases, and that will not give you much error. And therefore, we write that the confidence limits are P0, Z alpha, P dash gets changed by PO, P dash gets changed by PO, everything remains same, only P dash gets changed by PO, P observed, and that these two becomes my limits. But in all the cases, the way we are finding out the confidence limits, the approach is exactly same all the time. And if we solve a problem, example, a random sample of 500 garments was chosen from a production line and 25 of them was found to be defective. Calculate 98% confidence limits for the proportion defective. Solution, first of all we have to find out what is the observed proportion, PO. So PO is XO by N. XO is the observed number of defective items and that value is 25 and N is 500. So PO is 0.05. That means 5% of the garments are defective. We want to calculate the limits with 98% confidence. So 1 minus 2 alpha is going to be 0.98. So what is the value of alpha? 0.01. So what is the corresponding value of Z? For alpha 0.01, the Z value will be 2.3263. This is also from the Z table. This value will come. And we know the limits are this. In the previous slide it was shown. Just substitute the values now. 0.05, 2.3263, put all those values and you get the answer. This is your answer. 0.05 plus minus 0.023. These two will be the limits. So proportion defective is going to lie between 0.05 plus 0.02. So 0.07 on the higher side, 0.05 minus 0.02 if we took it, 0.03 on the lower side. So roughly we can say it is going to lie 0.03 to 0.07. This is the fraction. Or in percentage terms, if we convert, it will be 3% to 7%. So though the sample gives us a figure 0.05, means 5%. So sample data says 5%. So if we go for point estimate, so we should say it is 5%. But point estimate may not be correct. So you have to that's why we go for the interval estimate. The interval estimate, when you try to find out, we get these figures 3% to 7%. This is the interval, and we say with 98% confidence that it is going to lie somewhere between 3 to 7%. But what it is exactly, we do not know. That answer we will never get. Okay, with this we close this particular session, and you must read the slides again and again, and also try to solve some problems so that your understanding will be much better the more you read and more problems you solve. Thank you.